Which electrons do you think come off with relatively low energy? The valence electrons. So these are the valence electrons, and it's holding those electrons a little bit tighter. That's why ionization energy increases as you go across a period. In this video, we're talking about ionization energy, a trend, and then how to determine the ion charge based on ionization energy data. So let's just review our definition of ionization energy. Remember, that's the energy it takes to remove an electron to overcome those Coulombic forces that are holding it to the atom. So you can actually quantify this. When we've looked at PES data, we can actually determine how much energy it takes to remove an electron. So this is some real data for magnesium. So notice that first electron, what we call the first ionization energy, pretty small number. The second one takes a little bit more, but do you notice a really big jump between the second and the third? Like many times that value. Why do you think that is? Which electrons do you think come off with relatively low energy? The valence electrons. So these are the valence electrons. I'm just going to draw the electron configuration for magnesium for you, and then I'll show you which two electrons. So those two electrons that come off with relatively low energy are those two valence electrons. So why would that third one require so much energy? It's a whole energy level closer to the nucleus. So this is how you can predict ion charge, and here's these guys right here would form 2+ ions. These guys would form 1+ ions, and so forth. So let's get into the ionization energy trend. And this is a trend that you need to memorize. And what I mean by trend is as you go across a period, as you go to the right, ionization energy increases. And we're going to understand why. And then as you go down a group, it decreases. All right, let's talk about why it increases as you go across. Well, what's going on here? As you go across the period, as you go to the right, you are increasing effective nuclear charge. Remember the old Z effect? And it increases as you go to the right. Okay, because the distance between the nucleus and the electrons isn't changing much as you go to the right. But the effective nuclear charge is increasing, and it's holding those electrons a little bit tighter. That's why ionization energy increases as you go across a period. Now, why does ionization energy decrease as you go down? Well, look what's happening here. We go from 2s to 3s. Every time we go down one energy level, go down in a group, the atoms get larger and larger. We have valence electrons in a larger and larger energy level. And so that electron gets farther from the nucleus. And remember Coulomb's law, as distance increases, the force of attraction decreases. So let's take a look at lithium versus sodium. Well, which one has the larger ionization energy? That would be, looking at our trends, that would be lithium. Why? Because it's a smaller atom, so that electron is closer to the nucleus. Effective nuclear charge is the same in a group. Now, sodium versus magnesium. As we go to the right, what's happening here? We're increasing effective nuclear charge, and so we have a stronger force attracting those valence electrons. So memorize the trends and then be able to explain it based on effective nuclear charge and radius. That's the whole idea here. All right, let's look at one more. How about sodium versus chlorine? So what you're going to do is go to the periodic table, put your finger on sodium and chlorine, and figure out how are they related. Well, sodium is way over here, and chlorine is way over here in the same period. So what happens to the trend as we go across? Ionization energy increases. So it's going to be chlorine. Now why? As we go to the right, effective nuclear charge increases. Okay, so that nucleus is having a greater positive force, with about the same shielding, and so that attractive force pulling on that valence electron is greater for chlorine than for sodium because they're about the same size. I hope this helps you understand ionization energy trends. You can do this.